All right, good morning. Let me also start by thanking the organizer for inviting me here. I would like to tell you basically two different things related to graphene today. The first one is how you can induce a pretty strong spin-orbit interaction in graphene. And the second one, for which I will have much less time, so I will probably only tell you some of the basic aspects, but you can come and discuss after if you're interested, is the fact that close to charge neutrality in bilayer graphene and trilayer graphene, in fact we have done it, not in monolayer graphene, conductivity is entirely determined, if you have a very clean device, is entirely determined by electron hole scattering. The people who did the work are written here. For spin-orbit part is Zhe Wang, the main actor, and for the electron hole scattering part is Yang Gunam and Dongkun Qi are the main actors. So we have had important theoretical collaboration, especially for the spin-orbit part, and the materials that we use in this part came from Helmut Berger, who grew fantastic transition metal decalcogenides. Again, so these are the two topics. Let me directly start with the first one. I guess there is no much need to convince you that it's interesting to try to study graphene with strong spin-orbit interaction. The first topological insulator that was predicted theoretically was indeed monolayer graphene. If you include the effect of the intrinsic spin-orbit interaction, you have to add this term to the Hamiltonian of the free Dirac fermions, and this term causes a gap. And the problem is, the only real problem is that this gap is super small. It's like of the order of 24 microvolt in real graphene if you include only the spin-orbit that you intrinsically have in graphene, because carbon is a very light element. So it will be very interesting to find ways to preserve the property of graphene on one hand, but on the other hand to increase or induce spin-orbit interaction of a much larger magnitude. And so people try to do different things. For instance, they try to put graphene on pretty heavy metals like lead, and then you can indeed induce spin-orbit interaction. But what happens then is that you completely hybridize graphene, the state of graphene with the state of the metal, and you don't have Dirac fermions anymore. Another thing that people have tried to do is to create, to induce spin-orbit interaction by decorating graphene with, for instance, a heavy atom of heavy elements, or by inducing certain defects. And that also works up to a certain extent. But what you actually are doing there, you're degrading the mobility considerably. And so what we thought about is that, graphene is a 2D material, is performing best when you put it on top of other 2D materials very flat, like for instance boron nitride. And there is a class of 2D materials which is very flat, which are large gap semiconductors or reasonable gap semiconductors that you could use as substrate and have strong spin-orbit interaction. And these are the transition metal decalcogenides. So these are these kind of materials. If you look at a monolayer, a transition metal decalcogenides look like graphene. Is an hexagonal lattice with two different kind of species on the vertex of the hexagon. A transition metal typically is molybdenum or tungsten, and then the chalcogen, it's a disulfide or diselenide. And if you look at the band structure again of a monolayer, the bulk is more complicated, but there are some basic aspects. What you see is again valleys like in graphene, and the biggest aspect is that one of the biggest differences is gapped because the two atoms are different, but there is a very, very big spin-orbit interaction, and in particular in the valence band, for instance, the splitting between the two spin directions. So this higher energy valence band is spin in a certain direction, say down, and here is spin up. The splitting can range from 200 millivolts to about 400 millivolts, depending on whether you have molybdenum or tungsten compounds. In the valence band, in the conduction band, the spin-orbit interaction is smaller, but it's still pretty big. It's like of the order of 20 millivolts. So if you look at the monolayer, there is a lot of Dirac physics or gap Dirac physics with spin-orbit, which is interesting. That will not be very important here. The only point which is important here is from the physics is that there is a very spin-orbit interaction in the decalcogenides, and from the, say, more technical aspects, is that these materials are very flat and they are very good substrate for graphene. So these are the kind of devices we study. What you see here is an image. You see a whole bar on graphene, which is on the transition metal decalcogenides, which is these very flat crystals here. And everything is sitting on a substrate, which is actually acting as a gate. So you have a doped silicon oxide as a gate insulator. In this case, it was tungsten disulfide and graphene. So if you apply a gate voltage to the substrate, you can change the density in graphene in a certain range, because you can also accumulate charge in the at this interface in the tungsten disulfide. When that happens, essentially you are in this gate voltage region here, and you're not changing any more the density in graphene. You're changing the density here. And since tungsten disulfide has a much lower mobility than graphene, you see the conductivity saturating. But when you are on this other side of the gate voltage, you're changing the density in graphene, and you see the conductivity of graphene changing. As I show you in other devices, and especially with other decalcogenate, you can see both sides of the Dirac peak. Essentially, what you're seeing is the valence conduction in the valence band of graphene here. This is our first generation of devices, and then we work to improve them. So in this first generation, we basically took graphene, put it on the decalcogenates, did not do anything particular to increase the quality. The mobility was still pretty decent, it's like 13,000. We can get much higher now. And if you look at here, the quantum Hall effect, you see nice quantum Hall effect, exactly like you expect for monolayer graphene. So the quantization value are exactly what you expect for monolayer graphene, which means that we have Dirac fermions. So if we want to look at, so what we are interested in is whether now we have spin-orbit interaction, and we need to have a probe to look at spin-orbit interaction. And the simplest probe is to look at quantum correction to the conductivity. So if you take graphene not on the decalcogenites, but on something like, for instance, boron nitride, or if you do on silicon oxide, the quality of the graphene will be lower, but the physics will be the same. What you see is always, at low temperature, what we see is always weak localization. So if you measure the conductivity and you change the magnetic field, you see that the conductivity increases when you apply the magnetic field. Typically, it's not as simple as this, because here what you measure is, for instance, this is the resistance as a function of gate voltage. You have, if in these kind of small samples, you have sample-specific effect, you have to do an ensemble average. After you do the ensemble average, which basically means your average in the magnetoresistance are different, or the magnetoconductance are different gate voltages, you get this ensemble average curve, and this is what you see. So if you put graphene on boron nitride or on silicon oxide, you always see weak localization, meaning you don't see any effect of spin-orbit interaction. You can analyze it, extract interesting times, that's not the point here. Now, we do the same experiment, so we measure the magnetoresistance or the magnetoconductance of the devices put on the decalcogenates, and again, you have to do some ensemble average, because if you look here, you see sort of a single trace, a single gate voltage is something with very big fluctuation. You don't see much. These fluctuations are fully reproducible. These are what are called UCF, universal conductance fluctuation. If you now use the measurement at different gate voltage to average this trace, what you find is that eventually, after enough averaging, a magnetoresistance at zero field, you see it, a magnetoconductance. And now, contrary to what you have when graphene is on boron nitride, the conductance decreases when you apply a magnetic field. And now this is weak anti-localization. You see only weak anti-localization and not weak localization, which means spin-orbit, there is spin-orbit, and spin-orbit is pretty strong, because any trajectory has the spin fully randomized. So this was the first generation of devices on tungsten disulfide, in which we just basically did it and measure it and see and saw spin-orbit interaction. At the same time, we collaborated with Alan McDonald and his postdoc Hua Cheng, and they did ab initio calculation for the system of graphene on tungsten disulfide, and they find out that they expected that the Hamiltonian to be changed, the effective Hamiltonian at low energy of graphene to be changed by a spin-orbit term, which is written here. That's what they find by fitting their ab initio calculations. And there are two terms for spin-orbit interaction which are important. One is a Rashba term, another one is what we call a spin volley term. And according to ab initio calculation, the value of these lambda parameters, they depend a bit on the approximation they make, but they are of the order of a couple of millivolts in all cases. So essentially, this was interesting because it told us, yes, you also expect this spin-orbit interaction. You expect it to be pretty large. But at this stage from the experiment, we know that there is spin-orbit interaction, but we don't know what is the type. We don't know what is the term. We also don't know whether it's a band spin-orbit interaction or not. It could just be that the electron in graphene see the electric field of the tungsten atoms, which are, say, not regularly arranged. There is no commensurability between graphene and tungsten disulfide. So it could be that the spin-orbit we see is even just sort of an impurity effect. So it would be interesting to know what is the type of spin-orbit and whether it is actually a modification to the band structure of graphene. And so then to do that, we did more work, and we improved the quality of the devices. We look not only at devices on tungsten disulfide, but on other decalcogenates. One of the means that we use to improve the quality of devices is some sort of atomic sweeping. I mean, just when you clean the floor and you sweep, you go with your broom and sweep the stuff away. Here you can do the same thing with an atomic force microscope. This is a device very similar in concept to the one I showed you before. And initially, if you take an atomic force image, it looks sort of granular, and in fact, this is roughness, or it's dirt on top of your device. and you start to sweep in contact mode with your atomic force microscope, essentially you're sweeping the floor, you're sweeping your device, you're collecting all the dust here, and eventually this stuff is super flat. And you've thrown all the dust away, and actually if you make a larger scan image, you see all the dust piled up here. And it's amazing how that works basically always. And you see that the mobility increases substantially. So the highest mobility we get in this way was of the order of 200,000. So we passed from 15,000. It doesn't always work so nicely because you see there are also defects. Like if you have too many of these defects, it doesn't work. You need to select a flat area of your device, and then you can clean it, and then it works. So we then did, again, this is another example, dirty stuff, very clean at the end. We did this kind of devices on 3 different decalcogenate, tungsten diselenide, molybdenum disulfide, again on tungsten disulfide, but with higher quality. Now we see the Dirac peak in all cases. The most interesting case is possibly tungsten diselenide, because the Dirac peak is really in the center. You have a pretty large range of gate voltages in which you can explore the valence band and the conduction band. If you go too high with the gate voltage, you start to accumulate, again, charge density at the interface with the decalcogenates. But you see there is a pretty large gate voltage range where you're sure you're exploring graphene. You see beautiful Venn diagrams. So everything is fine and is under control. Like I said, highest mobility range up to 200,000. If you select a very large area and you don't clean it, you can go lower in mobility, which is good because you can also look at the effect of mobility on, for instance, weak anti-localization and check things as a function of scattering mean-free path. So with all the decalcogenates, we look at magnetoresistance. We only see weak anti-localization. In fact, if you want to do things carefully, you look at your conductivity, your magnetoconductivity. You subtract the value that you measure at high temperature, where phase coherent effects are basically very strongly suppressed. And this is the result. So only weak anti-localization, no weak localization. With pretty small magnetic field, again, because the mean-free path and the mobility start to be pretty good. That's not only true for the monolayers. All these samples are monolayers. It's also true for thicker samples. So like, for instance, this is a bilayer. This is a trilayer. You see beautiful quantum Hall effect in the trilayers, again, because the mobility is good. But the fact that the spin orbit is still strong because you only see weak anti-localization, no weak localization, as a function of thickness, for higher thickness, means that spin orbit really is quite strong, because spin orbit only affects the bottom layer. And so if you make your device very thick, at a certain point it should be diluted, in the sense that electrons should start not to see what happens at the bottom layers unless this is really rotating the spin a lot. And at least up to trilayers, that's the case. Even if you dilute by a factor of 3, it's still very strong. So we can fit the weak anti-localization in the monolayer. There is a theory with a quantitative formula due to Volodya Falco and Edouard McCann. And we can find, basically what we can find is an upper limit for the spin orbit scattering time. The data can always be fit, and this is the upper limit for the spin orbit scattering time as a function of elastic scattering time. So we find that basically this upper limit is always 0.2 picosecond, which is extremely short. And it is so short that the only possibility that you can imagine is that this is due to a modification of the band structure, because this is actually coming even shorter than the elastic scattering time. Now, you could argue if it is shorter than the elastic scattering time, your theory is not working, because the theory for weak anti-localization is in the diffusive limit, so you should be careful. And indeed, it's true, we should be careful. But this situation is not new. It has been seen before, for instance, in holes in gallium arsenide. And then the way to go about this is to try to find another proof of spin-orbit interaction, which is in any case useful, because weak anti-localization will never tell us what is the exact mechanism of spin-orbit interaction. And so the other mechanism that we look at is Schubnikow-Dirac oscillations. If you have a very strong spin-orbit interaction, then you split your Fermi surface, and you should see 2 frequencies in your Schubnikow-Dirac oscillations. And so the kind of things, the mechanism we have in mind is that you could have a Rashba term, or you shift your parabolas, or you could have a spin valley term, you shift them in the other direction. In both cases, you get the Fermi energy. You have 2 different values of kF, so you should expect to have 2 different frequencies of your Schubnikow-Dirac oscillations. Now, we did the experiment. For technical reasons, this is done on bilayers, not on monolayers, because you're much less sensitive to charge density and homogeneity. But then you see a bitting in high-quality devices. You see a bitting which is very, very clear. And if you take the Fourier transform of the Schubnikow-Dirac oscillation, you see a splitting, and the splitting depends on the gate voltage. And now we can analyze the gate voltage dependence of the splitting using the Hamiltonian that Alan and his postdoc Hua-Cheng had given us. And what we find is that, sorry for that, what we find is that essentially the data can most of the spin-orbit interaction can be accounted for by this Rashba term. That would be the red line here. But the data are also compatible with having a larger lambda term. So the red curve here is including a Rashba term of 15 millivolt. This is the red curve. Or I could have a Rashba term of 10 millivolt and then a lambda up to 6 or 7 millivolts. And this would be this dash curve. So to be able to discriminate between the situations, we would need to be able to go to lower densities, but then we don't see nice Rubin-Gus oscillation anymore, or we don't see the splitting anymore, so we don't have data point there. But the bottom line is that spin-orbit interaction is there. It has a magnitude of the order of 10 millivolt that we saw in different devices, and it is dominated by the Rashba term. So these actually, you see this band structure here. This is for the bilayers. This gap is actually not opened by spin-orbit. Is the gap that you open when you apply an electric field. However, in the monolayer, if you have both terms present, there will be a gap at the Dirac point. And the magnitude of the gap will be the smallest of these two terms. So it will be very interesting to see if this lambda really is non-zero, because if it is non-zero, there should be a gap at the charge neutrality point. It will be a small gap, and in a charge neutrality point, small gap is still much bigger than what you would have with intrinsic spin-orbit. And at the charge neutrality point in monolayers, effect of the fluctuation is bigger, so it would be still tough. But if it's something of the 10 millivolt, there is a hope to see some effect. So that's the end of the first part. I'd like to brief. How much time do I have about?
5, 6.
6, all right. 7? All right, so I'll go fast and we can discuss later if you have questions. So this is a different topic. So what we are looking at here is suspended devices. Suspended devices, if you are able to clean them, are the cleanest way of making graphene, and I think the cleanest thing of anything I've seen personally. So what you have here is a bilayer graphene suspended, contacted to 4 contacts. These multi-terminal devices suspended are not easy to make. They were not done before. A few years ago, we did them. We saw a bunch of things, including, for example, fractional quantum Hall effect. That's not what I want to talk about here. What I want to talk about here is something that we noticed. We thought it was nice because it showed the device was good, but we did not give enough all the attention it deserves, and that's what we did more recently. So if you make measurements in this multi-terminal geometry, you send current from 1 to 4, for instance, and measure the voltage between 2 and 3, what you can add, well, if you have diffusive transport, the electron will be injected and will reach contact 2 before we reach contact 3. Your resistance is positive, which is the normal case. But if motion is ballistic, the electrons are injected, they reach contact 3 before they reach contact 2, and your resistance is negative. It's just a negative multi-terminal resistance. So that's what we see here. As a function of density, we have a gate in the back. If I measure this resistance, this multi-terminal resistance, I see that at high density, the resistance is negative, so I have ballistic transport. At low density, the resistance is positive, I have diffusive transport. The charging, the Padlow's region is very small here. I mean, it's basically, I put it larger than it should just to show it, but we are certainly outside the region where charging homogeneity play a role. So initially we thought, oh, very nice, we see negative multi-terminal resistance. That's a proof that our device is ballistic, and stop thinking about it. But in reality, we should think a bit more, because the first question is, what determines this density scale? Why do we see ballistic transport only at 10 to the 10? Why don't we see it at lower density? And so to answer the question, we measure at a different temperature, and we see that we always see ballistic transport up to, say, 80 Kelvin, but we need to put more and more density to see it. And it's strange. When you have, so there are a couple of strange things here. The first one, this is pretty strongly temperature dependent, but photon scattering in this temperature range should not play any role in graphene. So what is giving the temperature dependence? And what is giving the density dependence? So what is the scattering mechanism, which is temperature and density dependence? And you get a pretty clear idea if you start to look at the crossover point. So there is a point where you start to see the negative resistance, and that means if you plot the density versus temperature, you get this data point. And this dashed line is the line which corresponds to having the Fermi energy equal to KT. So you have that the crossover is happening when the Fermi energy is exceeding KT. If the Fermi energy is smaller than KT, you have diffusive transport. If the Fermi energy is bigger than KT, is ballistic transport. Okay, these give a very clear hint to the fact that we are seeing electron-hole scattering, because if you are at charge neutrality, if the KT is bigger than the Fermi energy, that means we still have empty state in the valence band, and electron could scatter on those. If the Fermi energy is bigger than KT, there will be basically exponentially suppressed. The amount of holes in the valence band will be exponentially suppressed. So that was the the initial idea. And how can we check it? Well, we have to go in the diffusive regime and see whether we can explain the diffusive regime in terms of electron scattering. Turns out that that works very simply, and this is all the equation I will show you here. You just say your conductivity is due to both electrons and holes. The density we can calculate. If you know temperature and gate voltage, we know what are the densities. It's just because we know perfectly the dispersion relation for bilayer graphene. The mobility, we need to know. The mass, we know. The scattering times, in principle, we don't know. But if we assume that is electron scattering will be related to the inelastic scattering time that close to the charge neutrality is supposed to be given by kT over h bar. And then is not the total elastic scattering time, is only the scattering time for electrons to scatter on a hole, so it has to be proportional to the density of holes, and for holes to scatter on electrons. So if you assume this, you find an expression for your conductivity, which basically has only C as a parameter, and this density you can just calculate. You can, and if you look at the normalized conductivity, it depends on no parameters. It's only the mass you know. So either it works, either you put it on the data, either it works or it does not work. And if it will not work, I'll not be telling you this, but this is just the curves and the data. There is no fitting parameter. There is nothing you can change. You plot in log scale, is basically perfect. This expression, if you plot it, is just depending on EF over KT. Indeed, if you plot your data versus EF over KT, they collapse. And the theory matches the data as long as EF is smaller over KT is less than 1. Because that's the regime where you are charge neutrality. If EF is bigger than KT, you start to be ballistic. You cannot think in terms of a conductivity. So this is, we had 4 bilayer devices. They work at the level, all at this level of precision. We also had a tri-layer device. And a tri-layer is in principle a bit more complicated because you have a quadratic band and a linear band. But the linear band in this density range has a density of state which is less than 1% of the total density of state. So the linear band basically does not contribute to transport. So the theory should hold. And indeed, same story. Here, the mass should be 0.05 according to theory. We get 0.06. OK. So, but you see, even in log scale, the agreement is basically perfect. The only flexibility we have is to change this mass by a little bit. And again, curve scales. So if you have these very clean devices, close to charge neutrality is only electron scattering which matters, nothing else. You can also look at the absolute values. Here, of course, when you have a small device, you're going to have some uncertainty because current uniformity will not be perfect. But with no fitting parameter, no adjustable parameter, the data within a factor of 2 or 3, they are following the theory. Basically, we cannot change anything. This either it works or it doesn't. And I see that the chairman is getting impatient. So this is the conclusion. I told you about spin-orbit interaction in graphene, and I told you about electron scattering at charge neutrality. And I'm ready to take questions if you have any. Thank you for your attention.